So, hi everyone, I'm Dániel Gergely. I work as an Android developer, and I'm going to talk to you about how I built a 3D multi-platform game in Kotlin. The game is basically an endless runner. You are driving a floating car on a floating highway on the skyscrapers, and the goal of the game is to drive for as long as you can while avoid hitting the barriers. So the road is randomly generated. It looks pretty much like this, but also there is this queue mode where you can go around the road in a circle. The game supports 3 platforms. It supports web browsers, Android operating system, and desktop operating system. In terms of controls, it also offers nice variety. You can control the car with your touchscreen by tilting your device using the keyboard on Android and web, and on desktop operating systems you are limited to use your keyboard. So the first design decision was which graphics API to use, and I ended up using OpenGL because it's low level and I wanted to be in control over the finer details. So OpenGL stands for Open Graphics Library. It is available on almost every device, every operating system, and it has quite a few variations. OpenGL for desktop PCs, OpenGL ES for embedded devices like smartphones and televisions, and there is WebGL, which is a JavaScript API available in browsers. So even though there are multiple variations of OpenGL, they basically work the same, which is great because it would be a common approach to build a multi-platform application to write just the business logic once, and then the drawing parts should be written each time for each platforms. But with OpenGL you can do the graphics part once, and it will work on all of these platforms. So the next question was which UI frameworks should I use? And I ended up using these 4. So whenever I build a project, there will be some HTML and JavaScript files for the web. There will be an APK file for Android, and I use these 2 Java libraries. One of them is called Lightweight Java Game Library. The other one is called Java Binding for the OpenGL API. These are both cross-platform frameworks that provide the windowing system, provide access to the input devices, and provide the Java OpenGL API. So the next question was which language should I use? And no surprise, I used Kotlin because, as we all know, Kotlin supports both JavaScript and JVM as compilation platform. It also supports native as in machine code, but I haven't used it for this project, so I'm not going to talk about it. Having those targets is nice, but it's not enough. We still need a way to make it work that we just write the code once and it will run on all of these platforms. So we need a tool or method for that, and there comes Kotlin multi-platform, which is exactly about that. It's an experimental toolset which is in development by JetBrains, and the way it works is kind of inventing a new platform, even a new language, which is called the common platform. It is basically a template for how the platform-specific code would look like. There is one basic rule on it. You are not allowed to call any platform-specific API, but you can, of course, call other common Kotlin code like the standard library or other third-party libraries, which is nice. But what if you still need to depend on platform-specific APIs, or what if you need to design some code that works differently on each platform? And for that reason, JetBrains created this mechanism called the expect actual mechanism. A quick question, how many of you have used Kotlin multi-platform or this expect actual before? Not that much. So the way it works is that in the common code we define the signature interface of either a field, a function, or a class, and annotate it with the expect keyword, and then on each platform that you are targeting, you provide the implementation for them, and you annotate it with the actual keyword. So if you look at this example, let's say we want to be able to tell the time in milliseconds from the common source code, but it would require platform-specific API code, so that we create an expect function in the common source, and then we provide the implementations for each platform. And there we are able to use either this Java API or this JavaScript API. Another useful tool is actual type areas, which is nice when there is a class on a specific platform which you would like to use from common. Then we create this expect class interface of the common code, which looks exactly like that, and we provide the actual type areas for the platform which already implements that type, and then we also still need to manually implement it on the other platforms. In this example, I used sparse array because it is only implemented on Android and nowhere else. So in this example, if you want to use a sparse array in your Kotlin multi-platform project, and you don't want your Android code to have a sparse array implementation because Android already has one, you can use this tool. So now we know how common code turns into platform-specific Kotlin code, but we still need to know how Kotlin works together with each of these target platforms. So Kotlin for JVM is really simple to use. As we all know, Kotlin was basically created as a JVM language, which means that basically every Java type and every Java language feature has its Kotlin counterpart. The situation is not that simple if you are using Kotlin.js. Another big question, how many of you have used Kotlin.js? Same too. I have used. So basically there are three ways to call JavaScript API from Kotlin. The most elegant way is to use external declarations, which means that we provide also an interface of a fun or class, and we annotate it with the external keyword. It will tell the compiler that this API is available in the JavaScript context you are using, which practically means the DOM or WebGL from the browser. The other solution is to use dynamic type. It's basically just a way of telling the compiler to turn off type checking. The other solution is the JS macro, which suspiciously looks like a function call, but really it isn't. It takes in a string constant, and in compile time, it will just put that string into your JavaScript source code. And by the way, the output type of this JS expression is also dynamic. Let's look at some types. So as you know, since Kotlin is basically a JVM language, it's pretty simple in Java, but if you look at JavaScript, it's not all that pretty now. So you can see this number thing a lot of times. It is actually a 64-bit floating point number, basically a double, and JavaScript doesn't have any more numeric types, so it has to use it every single time. And the situation is especially sad in case of long. As you can see, long is represented by an object which has basically two integers in it, the lower and higher significant bits of that, which means it's not only very inefficient to use in terms of CPU, but in terms of memory management as well, because every time you make some long operation, the result of that will be another long, which is an object, which later has to be filled by the garbage collector. So if you are doing a lot of calculations in Kotlin.js, please avoid using long. But if you look at array types, of course, Java has them all, and for me it was a surprise, but JavaScript also has them. So basically JavaScript has no integer, but it has integer arrays, which is nice in terms of performance. I try to use these types a lot in my project. So now we know how Kotlin multi-platform works. Basically, the next question is how can we interact with OpenGL? And the solution for that is a library I wrote, which later became open source, and now it already has some community contributions. This library is called KGL. Its goal is to provide a thin layer, lightweight layer above OpenGL with as few features as possible, not to force any restrictions of the developer. The library basically looks like this. The most important part is this common source set and the four implementations. So just to give you an example, here is how the interface will look like, just a bunch of OpenGL functions, and here is how one of the implementations will look like, just a vector basically around, just an adapter around the platform-specific OpenGL API. So during development, I try to follow this pattern, but unfortunately, I couldn't just wrap the functions. Sometimes some more complexity had to be added. One of these challenges was to use resource identifiers in Kotlin multi-platform. By resource identifiers, I mean native OpenGL resources like textures. So on the Java platform, these are represented with native integers, but on WebGL, these are represented with objects. And the way I solve that is just to create expect classes for all of them and use actual type areas for integer on JVM and for any on JavaScript, which is neither of them is great if you are using them as either a Java library or a JavaScript library, but it is actually fine if you are using them as a multi-platform library, because then these types won't be interchangeable. So you can just say shader equals program or something like that, because the compiler will tell you that they are different. Another challenge was loading textures. In Java, textures are loaded using java.io.buffer object, and on WebGL these primitive array types are used. So what I did was basically just create another extra class called texture resource, which is something that can be used to load a texture from. And for now, only encoded PNGs are supported. And on Java, the actual type is a wrapper around an input stream, which is an encoded PNG. But on JavaScript, you can use the native type. So the other challenge was loading VERTEX buffers. Which like the previous challenges, there was a different type on JavaScript and Java, which I had to wrap. On JavaScript, there was a native array. On Java, there was a java.io buffer, and the solution was to create a type that is basically a hybrid, at least if you look at the interface. And on the Java side, it's a wrapper of a buffer. On the JavaScript side, it's a wrapper of an array value. So basically, here is how we can use OpenGL from Kotlin multi-platform. The next challenge was to do some calculations, for which I also created a multi-platform library. It's also available on GitHub. It has 5 basic types, 3 vector and 3 matrix types. They have all the basic operations you need in an idiomatic Kotlin way. So it has operator overloading, infix functions. It has also destructing and swizzling. Destructing is the operation you can see here, where you take apart a composite object into its parts. And swizzling is when you take parts of a vector and put it into another vector. And now it says XY, but it could have said like YZ or anything, and it would work. So let's look at how these types are implemented. There are a lot of keywords in here, so let's go through them one by one. So it is backed by primitive float array, which is good for performance, especially in JavaScript. It is an inline class for performance, which means that when this back2 type is used, it doesn't actually get created, only the array gets passed around. So it's nice, one less object to work with. It has an internal constructor for type safety, which is obviously necessary. We don't want anybody to use this constructor with a random value, for example, an array with an incorrect length. And if you look at that suppress at the top, it is necessary because Kotlin right now doesn't allow internal classes to have non-public constructors. So I just suppressed it, and I hope it won't break in the future. Maybe it will. And operators are implemented as extension functions, so they are not part of the type. And if you look at how calculation functions are implemented, which are also part of this library, for example, if we want to calculate rotation matrix, we have basically 2 ways to implement an API for that. Either to return a new instance of the object containing the result, or take in the result object as a parameter and write the result into that. And this first one, I think, is much more readable, and this later one is harder to read, harder to write, harder to maintain. But unfortunately, when you are writing a high-performance graphics application, you have to be aware of the performance implications of each one, and this one creates a lot of garbage, and the garbage collection makes the performance unstable. So the way I developed the game is by starting with these ones, and I experienced that the game was running very slow. Looked at the profiler, looked at where these objects are coming from, and I replaced the most critical ones to these ones. So in this one, a field is already created, and that field is used every time to store the result of the operation. So it's time to start talking about how does the game actually look like. The project structure looks something like this. It has two main parts, which are 4 application projects, which are just normal applications, no multi-platform involved, and the game library, which contains both the logic and drawing for all of the platforms. And the question is, since KGL is an interface, and this library needs a KGL interface instance to work with, where does it created, how does the library get this instance, and for that I needed to make the structure a little bit more complicated, but there's a system in here, so if you are able to find it, then it's not that complicated. So if you look at each application project, all of them are depending on a single KGL module and a single game library module. So the way it works is the application knows how to create this KGL instance, and then it will pass to the library. And basically, this is how the game library and the applications communicate with each other. So the first interface defines all the methods that the library, the applications need to tell the library. For example, the first one is that the surface is created, time to load some resources, time to initialize your site. The second one is that the size of the surface has changed, time to do some calculations. The third one is the most important, that now it's time to draw, please draw everything that is necessary, and the tools and resume methods are only needed for entry, so that if the user presses the home button, then the game won't just go on. And this second class defines all the dependencies that the game library actually needs to run. And well, let's go through them one by one. So the first is resource provider. The way resource loading is handled, by the way, by resources, I mean static resources that you have to load, like PNG files for textures, text files for models, and sound files. So each resource is identified by a string. The resource is ordered hierarchically, like in directories. And an important requirement was that each time I tell Gradle build, it will pack everything necessary, and I know that both the APK and the jar files will be working. So the way I solve it is, in case of desktop Java applications, they are just put in the assets directory, and that is also the case in Android. And in case of web, just upload it to a server, and then the game will be able to reach them using an HTTP request. But unfortunately, it wasn't that easy, since these I operations should be done asynchronously, and different platforms has different ways to provide you with async solutions. For example, on the JVM, we have threads, we can basically do whatever we want, but we have constraints, like the OpenGL API calls must be done from a specific thread, and also on Android, I operations cannot be done on a main thread, we have to do them on another thread. And on JavaScript, we don't have threads, we only have an event loop, and we only have async API for every I operation. So the way I solved it is by creating this monstrous future interface, which is actually kind of a mixture between Alex Java and Future, and maybe an async task. Maybe I could have gone with coroutines, but at that time they weren't working for me. I couldn't get them to work, so that's why I stuck with these solutions. So now that we have this interface, you can define the resource provider interface, which looks like this. Each kind of resource is returned wrapped in a future object. But still, there is this question: how to actually create this future object that will work correctly on each platform. So there are basically two ways to do that. On Java, there is usually a synchronous call, which we wrap in a runnable. And the way that I use to create future objects from that is, first I define an executor interface, and then this future from runnable function, which needs two executors. The one is which executor should actually do the operation, and the other one is which executor should the callback function run on. And the resource provider implementation of Java looks like this. It needs an IO executor and an OpenGL executor, and the actual operation will run on the IO executor, and the callback will run on OpenGL executor. On JavaScript, as I said, we have asynchronous API, and the way we wrap an asynchronous API in the future object is, I define the dispatcher interface, which has two methods, completed and failed. And whenever we want to create a future object, we get the dispatcher instance, we start the operation, we subscribe to the operations callbacks, and in the error branch we just call the failed method on the dispatcher, and the success branch we call the completed branch of the dispatcher. So basically this is how all of the resource loading works in the game. Next one is input service, which is actually pretty straightforward. This interface should be implemented by each application, and then the instance gets injected into the game at start, and the game can now use these methods. one thing that I had to be aware of is that I defined unified coordinate system for the game, which is to use values from 0 to 1 on both axes, and it was the application's responsibility to convert from their own kind of coordinate system to this one, so that the game shouldn't have to deal with that. Next one is sound service, which was used to preload and play MP3 files on web. The HTML audio element was used on Android. The built-in media player was used, and on desktop library, I used a third-party library called J player. And the interfaces look like that. The sound resource was this OPEC type, and then once we fetched this sound resource from the resource provider, we gave it to this thing called the sound service, which created a sound player object, and the sound player object was the one that we could actually use to play the sound file. Next is vibrator service, which is super simple. It can vibrate for given amount of time. So this is how these services work. Now it's time for some demo. It works. So this is how the game looks like in the browser. That's some nice menu. I will turn off the tutorial now because I know how to play. You can see it runs at a smooth 60 frames per second, and basically that's the game. But it's not that easy as it looks. It looks easy for now because it gets faster. So I hopefully won't die until I can show you how this tube mode looks. Now it's getting closer.
Oh, yeah.
And here is the transition.
Well, you're actually good at your own game.
So, up here this point.